Okay, looks like we're live. Quickly closing that to avoid a regress. Welcome everybody to the second Paperathon. Um, this is just going to be in a very similar format to the first one, which was a very informal read-through of a number of papers together with input from the chat, questions as we went, going through a bunch of different papers, in this case related to the pipeline from data through pre-training, fine-tuning, and preference alignment, whatever you'd like to call it. So you can see here is the document from that first Paperathon. We ran through a number of papers, and while we went through, everyone was making notes and sharing comments, etc. in a nice shared Google Doc. So we're going to do that again. So I will copy the link into the chat, if I can find the option. And I'm going to be monitoring chat the whole time, hopefully enough to surface anything like questions, comments, and queries. Give it a second or two. There is some latency between actually streaming and when things show up on the live stream versus when I see them in the chat, so be mindful of that, but hopefully I'll be able to keep an eye on that and make sure that we don't miss too much. If you're curious where these papers are coming from, in this case today, it's less of a general theme versus the previous one, which had more planning, and more just going through my backlog on Zotero of things I'd like to read, which I've either read a while ago and want to revisit, or which I haven't gotten around to, but have seen cited enough times, or have seen referenced recently, that they're back up towards the surface. So this link here actually goes to the library where myself and some fellow researchers keep a whole list of papers that we found relevant to the kinds of research that we're doing and just our general reading. So you can sort these however you like. This is a public library, I believe, so you should be able to go and see. I think it's approaching 1,000 papers that we found. Not all of us have read all of them, obviously, but today is going to help me get a little bit of a head start on some of the recent ones that have been added. At least most of them should be in that library. If you are in the chat and you can see this, feel free to chuck a note in there so that I know that other people can see it. And then also feel free to join the actual Google Doc. What we're going to do is for every paper we look at, I'll put a heading with the title and the link, and then we can collaboratively make notes from there. Okay, so I should also mention the general theme of today is going to be very language model focused, but we are going to be starting with a couple of papers that are not language models, but that I thought were fun nonetheless. And that'll be a good warm-up that'll give people a chance to join, and then we can switch gears and focus on the language modeling papers together. First one that's going to be a brief look is scalable pre-training of large autoregressive image models. So I'll switch over to Zotero. You can load that up however you like. And this is a nice one because we're not going to spend much time diving into technical details. We're just going to appreciate the good engineering work done by, in this case, a team at Apple, scaling up the same types of ideas that we use for language modeling and applying that to images. And so their figure one that they lead the paper with before even the abstract, scaling behavior as we scale the capacity of these large models, we observe improved performance, which directly correlates with downstream performance. So this pre-training performance gets better, and that directly improves the downstream performance as you scale. And you can see this graph does not look like it's stopping at the largest scale that they test. Neither does it stop at the largest amount of data that they show. So this is very, very reminiscent of the early days when people were trying this kind of scaling very successfully on language models and finding that we keep making them bigger, we keep feeding them more data, they keep doing better and better at downstream tasks, and that's exactly what this paper does. So inspired by large language models, we investigate their autoregressive image models pre-trained with a fairly simple objective, and show that they have very similar properties in terms of getting better as you go larger. Okay, so they do various tests on that. Let's skim through and try and get an idea of A, how they're training, and B, what this looks like. Okay, so they're training on a large data set of images, and in fact image text pairs filtered from Common Crawl. They are following what is like a language model objective on image patches. So rather than pre-training with like a masked autoencoder where you're trying to generate some sections of the image, or some kind of contrastive loss where you're trying to do different transforms of the image and map them to the same space. They say, what if we just take a very simple top left to bottom right, treat the image as a series of patches, and try and predict the next patch. So this is a very nice simple take. If any of you have read the Fuyu paper, you'll see that their approach is also like this. Just feed the image in patch at a time, feed any text in a token at a time after that, and use the same autoregressive objective for everything. And that's going to give you the ability to train on images or text, or images with text. Very, very scalable and easy objective, no fancy tuning, virtually no priors, just going top left to bottom right. So I really like that, nice and simple. And yeah, they make sure that during training you are only looking at the preceding image patches. So for predicting that the next token here, the next patch here rather, actually let's look at an example. So from this patch 7, we can look at all of these preceding patches above it and to the left of it if there were any, but we can't look further in advance. So that's the pre-training, and then for downstream tasks, what they're going to do is they're going to use the features or the backbone as a whole, feeding the whole image through, and then adapting that somehow. So let's check if we can see exactly how they do that. Prefix transformer. Oh, okay, so they're saying, that's a detail I missed in this diagram. Rather than it all being this autoregressive prediction with the causal masking, they have some prefix section, some number of tokens that they allow to attend to each other forward and backwards. That makes sense. That lets these early patches attend to each other and produce features that are informative for later patches without this need for this like causal masking where each one only looks at the preceding ones. So that's the part that's going to be used to build useful representations for your downstream task. But you're still able to do this predict the next patch in a sequence prediction type loss for everything after that prefix. Okay, and then MLP prediction heads. We have the body of the transformer, and then right at the end of that we have the MLP that's predicting, in this case, the pre-training objective, what's the next patch. We can remove that, keep the body of the transformer, and then we can slap on a new classification head or something like that. In blocks of MLP on top of the final transformer layer, and that's what they use. Okay, so for classification, they don't do anything fancy. Okay, yeah, so they only train a classification head, so they're not continuing to train the bulk of the transformer layers once they're adapting it to some downstream classification task. Okay, so the loss goes down as you pre-train for longer. That makes sense. The ImageNet top 1 accuracy increases as you pre-train for longer, and you can see starts to flatten out, but as you go to the next model scale, from 0.6 billion to 1 billion to 3 billion to 7 billion, you get a jump each time as you scale that model. And then also the more training you do, the higher the accuracy. Both make sense. Cool, okay, they have some idea of dataset size and saturation here. So this pink line is ImageNet 1K, I'm guessing. IN 1K is ImageNet 1K. So if you continue to train on that same dataset, at some point you're going to hit a floor, right? We've seen multiple copies of this dataset now. Maybe you've done, some fairly high number of epochs. It ceases to be that useful, whereas their 2 billion parameter dataset, much larger than ImageNet, continues to give dividends for much longer, and something about this dataset makes it the plus version. It gets even better. So let's see if we can find out what the difference is there. Okay. So this DFN2B plus is their original dataset, but also including some ImageNet images in there as well. And since the downstream task is ImageNet classification, having the mixture of in-domain data plus high-quality out-of-domain data, I guess that gives it the extra boost for the downstream accuracy. So that would make sense. Although they don't even show the downstream accuracy here, maybe it's just that that's an easier dataset because you have more of the ImageNet mixed in. Okay, and then, yeah, the more compute you put in, the lower the loss. That's all pretty standard scaling stuff. We'll look a little bit more at scaling later. But yeah, that seems to be a pretty solid paper. They've scaled their models a lot larger than most ImageNet papers tend to, the older ones at least that I know of. But yeah, we can see on a bunch of data sets they're not always the top. DynaV2, also an excellent paper, does pretty well, but it's fun to see something that's top or close to top coming out of this fairly simple compared to the more complicated pre-training styles for images objective. Yeah, doing pretty well across the board, edged out maybe by one or two models that are also quite large. But yeah, apart from that, doing a lot better than some of the older approaches. So very nice to see. Kind of funny that scaling continues to work so well. But yeah, I thought that was a very well done paper. I'd only skimmed it before, nice to take a slightly closer look. And good to see that people are still working on image understanding, and I bet starting to think about how you could combine this with language modeling, because this says let's take the ideas of language modeling, applies just to images, but I know there are people excited about, well, why don't we just train on both from the start? Alright, that's one of our two warm-up image papers. I'm just going to check the chat on another device to make sure that I'm not missing anything. I see Jesse Andrews is here and saying looking forward to the DSPy part. Yeah, DSPy is a little ways down the menu, but maybe we can maybe we can bump that up before some of the reward modeling parts. That might be might be a good way to go. Or Jesse, if you've got a lot of patience and time, you could wait. I am very appreciative and happy that people seem to enjoy this Paperathon format. For me, this is a lot easier than planning a video, especially now that I have a full-time job to work around. Yeah, this takes a lot less time on the prep side than something like a more focused single topic video. But people seem to appreciate just being able to casually follow along with a longer stream running through a number of papers, put it on in the background, etc. So yeah, I really appreciate the people who've reached out to share that they're enjoying this. And yeah, I'll continue to do them every now and again, I think, as we go, and hopefully the format will be refined over time. Okay, so any one note from this, scaling works. If you have more thoughts than that, please do add them in the document here. It'd be nice to flesh these out. Otherwise, what I'll do is after this, I will double speed, play through the recording for myself, and make some notes while we go. So this document should stay as a living, updating document, at least for the next few days, and then be linked in the description of the final video. Great. Alright, moving on to the second paper on our menu then. Scalable high-resolution pixel space image synthesis with hourglass diffusion transformers. And this one, I don't know that I want to read it on the stream so much as make people aware of it if you haven't seen it already, just because this is very exciting. This is work from Catherine Crossan, who was one of the early and extremely helpful people to be figuring out how to make diffusion models work at all for image synthesis in the open source world. So when OpenAI had released Clip and the first few diffusion model papers started coming out showing that they maybe had promise for image generation, Catherine was one of the early people saying, well, can we do clip-guided diffusion? She invented a number of key techniques around that. How do we steer these models? How do we build them? Implemented K-diffusion. Her K-diffusion repository was excellent code for diffusion modeling. And a bunch of other people in this team as well, Birch Labs, my friend Tanishq, some people from Stability and elsewhere, Medoc, I think some of these researchers are maybe involved in. Anyway, it's a great team of people in the open source world doing good things to push image generation forward. And in the previous one, we looked at some diffusion model papers. So this is presenting a scalable way to do pixel space image synthesis. So no need for separate autoencoders, no need for crazy convoluted architectures where you have multiple stages or cascading super resolution. Can we do just pixels in, pixels out diffusion models in a way that's not wasting a ton of compute, that scales up to nice high resolution and that gives good results? I think the answer that they provide seems to be a solid yes. Okay, so they present their hourglass diffusion transformer. It works directly in pixel space up to 1024 by 1024, builds on the transformer architecture. So again, just like Apple's work, rather than reinventing the wheel, why don't we take this well-known building block where we have something that we know scales up well and continues to get better and better as you scale, the transformer, find a way to adapt this to a specific task, and then apply this, in this case for image synthesis with diffusion models. So let's skim down to the architecture here, and you'll see this is a lot less moving pieces compared to some others, but there are a lot of nuances in here as well. Okay, so we have an image input, patching and embedding. Again, similar to what we saw here, we're mapping these image blocks into like one patch of the image becomes some representation. And then here we have these HDIT blocks. And these blocks are the transformer blocks. That's the main part of this architecture. But you'll notice that there's two types. There's neighborhood HDIT blocks, and then there's these global blocks. And that's the trick here, is that we're doing something that looks kind of like a U-Net, right? We start with an image, we project down, process, project down, process, project down, process, and we have these skip connections. But yeah, the insight here that comes from some other papers and also a lot of experimentation that the team has done is that we don't want to waste too much of our compute at these high resolutions, and specifically we want to avoid trying to do attention across a large sequence or a large image with many, many patches. And so the other part of this, apart from like, okay, we've simplified the architecture, we figured out how to do, nice training schedules and everything else that they iterated on here. One key insight is to say, well, we only need attention in this center here, where we have a much lower resolution representation, and then we can globally attend to all the different patches in that representation. But at these higher resolutions, we're instead going to use neighborhood attention. So we're only going to incorporate information for a patch from its direct neighbors. Okay, so the hourglass architecture hierarchical implementation. Let's see. Yeah, I think that's the main part of this paper that I wanted to highlight. They have lots of other things that they adapt from other works, just general good best practices for training diffusion models. Here's more information on the actual block. Position embedding. You have way of feeding and conditioning, and you have our multi-headed self-attention. Oh wait, yeah. So this is their variant. Sorry, this is the DIT block. This is the HDIT block, and presumably somewhere in here is going to be the way that you can switch between self-attention that's like global self-attention versus neighborhood. Cool. Anyway, yeah, I've realized that we probably shouldn't spend too much time diving too deep into diffusion weeds, but this is a relatively small data set in terms of number of images and a relatively small model, high resolution and fantastic results. Class conditional ImageNet, again, small by some of the recent diffusion model standards, no classifier free guidance or any tricks, and extremely good samples. No pre-trained autoencoders, no fancy multiple stage super resolution. Yeah, very, very compelling work. I look forward to seeing a larger text condition version. Hopefully sometime in the future someone gets around to training that. Okay, so if I was to go into our notes here, again, I'll start making some proper notes a little later, but for this one, also if we had to summarize in one word, there we go. Okay, so that's those two that I had still open in my Zotero needing a final look before they get put away. So now I'll take another break, check the chat again if there's suggestions. Otherwise, we will start diving into language modeling. And there is a rough broad strokes. Oh, and I've remembered I should do more diagrams because people liked the whiteboard diagrams. So we'll switch gears a little bit. We'll spend a bit more time now as we go through these papers a little bit more in detail. And yeah, hopefully have any questions or notes from the chat trickling in. Yeah. Cool. I don't see anything coming up just yet. I hope I'm not missing any. Cool. So into language model mode we go. And we have a sequence of 3 papers looking at, yeah, I'd say if we remember the framework from the previous Paperathon, we had this general pipeline of like, where do we get these large models that we end up using? We said there's a whole process all the way from the data through the pre-training, fine-tuning, preference fine-tuning, and final use. Yeah, so this next 3 papers are all in this sort of region. How do we take a pre-trained model and make it better, more useful? And sorry, I've just seen some chat. Yeah. Okay, great. Yeah, how do we take a pre-trained model, make it better and more useful, and continue improving from there? So first paper, self-rewarding language models. I'll put a little title in case you would like to take notes as we go. And this is by a team from Meta, I believe, yeah. Published in January, so maybe 2 weeks old, pretty ancient, but very interesting nonetheless. Okay, and I'll make sure you can see this. This one is one that I don't think I've read, so we're going to have to go through a little more slowly. If you have insights, please chime in the chat. We posit that to achieve superhuman agents, future models require superhuman feedback in order to provide an adequate training signal. Bold opening. In other words, the scaling from human feedback is limited and I guess expensive. If you've seen some estimates of how much Meta spent on the human feedback for Llama 2, I think that cost probably maybe matched or even outweighed the GPU cost of those models, was just the human labeling and the labor in general that needed to go into that. So they're saying in the future, we need better signal, more signal than we can achieve just with humans. And so that could be a bottleneck, both in terms of the amount of data you can get, and also humans only have some level that they perform. And so, yeah, that's a limitation for us going forward. Okay, they also say that separate frozen reward models cannot then learn to improve during LLM training. So if you only train a reward model once at the start based on human preferences, and then you try and use that for further training, that frozen in time model can't learn the new types of completions and any nuances there. In this work, we study self-rewarding language models, where the language model itself is used via LLM as a judge prompting to provide its own rewards during training. Okay, so we're trying to use a single language model to both be the judge that's evaluating in place of a human, and as the thing that we're continually optimizing. We show that during iterative DPO training, that not only does instruction following ability improve, but also the ability to provide high quality rewards to itself. Okay, so this is building on DPO, which we looked at last time, direct preference optimization, but we're also now using, for the samples that uses, we're using the language model itself as a judge. And it's somewhat surprising that you're using the same model for both. In many cases, you might be a little bit worried, what if this just starts to go off the rails and things just get worse and worse because the model that we're updating, if we update it badly, that might then be a worse judge, and then you might just get progressively more and more garbled. But they say actually, counter to that intuition, if we repeat this, it gets better and better at producing, following instructions, but it also gets better at judging. So they're fine-tuning Llama 70B, they do 3 iterations of their approach, and they find that it outperforms many existing systems on Alpaca Eval 2.0, including some state-of-the-art closed source models available via API. Okay, so while only a preliminary study, this work opens the door to the possibility of models that can continually improve in both axes. Very exciting, very bold abstract. I can see why this paper got some people excited. Yeah, so let's dive in and see exactly how they do the magic. Cool, we're not going to read the whole intro. Iterative DPO, starting from a seed model as shown in figure 1. In each iteration, there is a process of self-instruction creation, where candidate responses are generated, and then assigned rewards by that same model. They have this LLM as a judge prompting, which we'll try and figure out what that is, which is also an instruction following task. So I guess that's hinting there that if this model gets better at following instructions, it gets better as being a judge. They build up a reference data set from that generated data, and then they do the next iteration via DPO. Okay, so we generate some prompts, we seed the model, we generate responses, we generate rewards, all with the same model. And that gives us a new set of data that we can use for generating. We train a model on that using DPO, and then we go back to repeat. We generate more responses, evaluate them, we have a new data set, so we train. We generate more responses with the new model, generate more responses, evaluate them, give them rewards, train again. So it's this feedback loop here that is this continual like self-rewarding and improvement. Okay, so some questions that I have off the bat. Yeah, one, the specifics of how they do these rewards. And I think DPO, yeah, they say preference pairs. So this is a set of completions where one is definitely better than the other. And so we'll see how they map from, is it one reward per completion to get these pairs, or do they feed in random pairs to the model and say which of these is better? Yeah, and we'll see how they start, like how do you figure out what types of thing to generate here? What is the input, if anything? So let's go and find those details. Okay, initialization. So they have a seed set of human author data, instruction, prompt, response, which they'll call instruction fine-tuning data. Okay, so that might be something like the alpaca data set that was generated by language models. So never mind, this is human authored, so something like Dolly maybe, and that's going to be the base. And then they also have a seed set of evaluation instruction prompt, evaluation result response examples. Okay, so this is some custom written, let's teach it how to be a good judge instruction following data, which you could get away without if you have a good general instruction following model. But yeah, if you throw in some example instructions that include judging instructions, you'll get a model that's better at judging instructions. That makes sense. And so this is a way to also like seed it, I guess, with some human preferences. Here's an example of a response. Here's what it was judged as based on some reasoning. Oh, this was a very violent response, and it was also incorrect because of X, Y, and Z. Therefore, this is a very bad response. So that's one of the ways in which you'll be seeding some kinds of preferences to this model. And they showed they have some format for these prompts. And these are going to be like the initialization. Okay, then we can self-modify the training set, generate a new prompt with few-shot prompting, generate candidate responses, and then evaluate candidate responses. Okay, so we start out with some demonstration data, and then once we've done some training, we can continually generate more by saying, here's 3 examples of a prompt, create another example. So presumably if your initial data is not that diverse, you might be limited because you might generate some new types of prompt and new types of instruction, but they would probably be quite close to the examples that you have. So yeah, it would be interesting to see how much diversity you need in your original set of seed instruction data. But I guess these models can be creative because they're pre-trained on very diverse data, so maybe they are able to generate novel prompts. Okay, and then the feedback. They have pairs of data. Winning and losing pair is used for DPO. They also have a positive examples only variant. Okay, so this is where you could say, I'll also like maybe keep the best example in each batch that just goes into my like general fine-tuning data. And I can just fine-tune on that like a normal language model. I don't need any DPO or any RL stuff. Cool, this is how they do the judge. Review the user's question and the corresponding response using the scoring system. User response, justify your answer, give it a score. Okay, that makes sense. Okay, and there's other works apparently that have looked at this kind of iterative training, but they use an external reward model that isn't updated. And so the key thing here is that as we're training our model to follow instructions better, we are then also using the resulting better model as a judge for the next round. That's like the key part of this, self-rewarding language models. Makes sense. They use Llama 2. Oh, they use the Open Assistant dataset. Oh, that's lovely. Okay, so that's a nice open dataset rather than any internal meta thing. Fantastic. 3,200 examples. Only the first conversational turn. High quality. Nice. And then for evaluation, they use GPT-4 as a scoring method, following alpaca eval. Might be worth looking at the alpaca eval evaluation. So I'll flag that as a potential thing to add to the queue. And they report results on the leaderboard format and compare the win rate. Very cool. Okay, I don't think we need to go too much into the training, but here's some key figures. M1 versus M3, M3 versus M1, M2 versus M1, M3 versus M2. And in all cases here, the later model is beating the earlier model, rather than vice versa. So this is like we're continuing to improve. The third iteration versus the second wins 47% of the time, ties 40% of the time, and only loses 12.5% of the time. And comparing to the fine-tuned baseline, the first iteration actually is about tie, maybe slightly worse than the baseline. But after another iteration, it's already markedly better. After 3 iterations, it's markedly better. I'm curious why they only show 3. I guess maybe that was enough to show the trend, but I'd love to know, does it keep improving? 4 or 5, what does it look like? Does it tail off? Yeah, kind of surprised that that's not anywhere I can see so far. Yeah, their alpaca eval win rate over GPT-4 Turbo as evaluated by GPT-4. So that's a very hard metric. They go from 9 to 15 to 20%, and that puts them roughly on par with Mistral Medium, beating Claude 2, Gemini Pro, earlier version of GPT-4, GPT-3.5 Turbo, and the Llama Chat version, which was their RLHF attempt previously. So a nice big boost on this new eval. Yeah, and nice to see that in general the quality is improved. And this is the reward modeling ability as well. Okay, so we'd also expect this hopefully to go up given what they've said. Pairwise accuracy continues to increase after multiple levels of fine-tuning. Fantastic. Yeah, cool. Great. Okay, so that seems like a nice solid method, self-rewarding language models. Very cool observation that as you train a better instruct model, you have a better labeling tool than you did before for ranking or evaluating responses. So you should use that rather than some sort of static reward model to work on generating your next set of data for the next iteration. Let's see if they mention anything in limitations about only trying 3. Okay, so maybe this is just this is what we did rather than we tried every single thing paper, which is fine. And leave yourself some work for future papers. That's also okay. Fantastic. Are there any thoughts or observations or questions that people have watching? Great. Okay, so that was self-rewarding language models. The next one we're going to do, in a similar vein, honestly, is here because I found it while I was looking for this paper, but it looked interesting as a comparison slash counterpoint. Self-play fine-tuning converts weak language models to strong language models. So let's see. Yeah, this is a little, a week or two before this self-rewarding language models, different team, but maybe, yeah, shows that this idea has been floating into the zeitgeist. How do we use language models to improve themselves? How do we get away from human annotated data? Yeah, without the need for acquiring additional human annotated data. It's obviously something that many people are thinking about, and it's fun to sometimes see different attempts at the same problem. Okay, so we propose a new fine-tuning method called self-play fine-tuning, which starts from a supervised fine-tune model. It plays against instances of itself, generates its own training data from its previous iterations, refining its policy by discerning these self-generated responses from those obtained from human annotated data. Okay, so like the self-rewarding models, it's generating data for the next iteration, but the objective here is a little different. It's almost like a GAN. It's trying to spot which are the LLM generated versus the human generated ones. Interesting. So it's more like an adversarial loss in a way. And so this is going to try and follow the data distribution of the training data exactly. They evaluate on different leaderboards. They show that it improves the performance on a lot of different benchmarks. Fantastic. Yeah, so let's see exactly how they do this. Okay, here we go. High quality data set. Okay, we're doing the RL notation, I guess, some policy. We evaluate this against the baseline, against the data set. And we notice that there's a gap between the ground truth response from the dataset and the LLM generated response. So this disparity says that we're still got room to improve. We're not perfectly mimicking the training data. Okay, let's see. I'm wishing for like a one big diagram explaining how this thing works. Here, okay, we've got a model generation, ground truth completion. Oh, okay, and they're saying somehow this one is closer to the chosen ground truth, so it's better after iteration 1. Great, that doesn't tell us how we do that. This is a lot of notation. Okay, this is kind of what I wanted. I didn't like the verbosity of those paragraphs. So we're going through some number of steps T, and within each step we're generating some synthetic data, in bits of synthetic data. We're updating our model to try and minimize some function of the difference between, this is a likelihood of the completion versus the likelihood of the actual data. It's a pretty confusing formulation, but let's see. Is there any like step back and explain this anywhere? Maybe we should look at the results to see how much we should care about this. Okay, so starting from a fine-tuned baseline, their method improves and improves and improves and improves. So that's a good sign that this is useful. Starting from a decent fine-tuned baseline, and they use that same data set to generate synthetic data. Training on that data for longer doesn't help, but their spin method does, even with much less data. Okay, so this looks very promising. Maybe we should go back to the methods section and try and figure out. Maybe there's a better summary in the introduction of exactly what's going on. Okay, so we take some data, we generate some new completions, then we train a new model that's somehow trying to prefer responses from the original over the generated. So we doing effectively something like DPO, but where the correct or the highest rated or the preferred one in the pair, just like in this one had these preference pairs, is kind of like that's our original ground source human data that we're trying to get closer to, and the negative one is the LLM generated one. So you're saying, oh, try and move away from your LLM sounding one and more to the original data distribution. So I'm not quite sure how we fine-tune it to prefer responses, whether that's something like the using the likelihoods. Maybe that's the case, but we'll have to check at that. Once you've done that, you've now got a model that prefers to generate things that look like the data versus things that look like the older version's generations. So hopefully it generates things that look more like the data than the previous version. You then repeat the process again and again and again. And hopefully as you do this more and more, it just looks closer and closer to the data. Okay, so that seems to make sense. They say, oh yeah, it's similar to the DPO method, but instead of having two preferences where one is better as judged by a human, like in DPO, or two preferences where one is better as judged by an LLM in this paper, self-rewarding language models, we now have two completions, but we assume one is better because we know it's better because it's the original data. And we say the generated data probably isn't as good, where good here means just like the original data. And so that's where you get these pairwise inputs. It's just saying whatever we generated last round, that's probably good, but it's not good enough because it's not exactly like the data. And so somehow we'll like keep that ranking. And the self-play, yeah, is similar to a GAN in that you've got some part of the training that's trying to spot fake from real. Cool. Okay, I'm not going to try and go through the notation unless someone in the chat is extremely excited about that, but I do think that's an interesting idea, an interesting paper. Yeah, and a nice take. This is kind of opposite to the previous one that we looked at in that it's treating human data as the gold standard, that we're going to keep trying to get closer and closer to that human data, whereas this one is saying, oh, this human data is obviously a bottleneck, and it's like keeping our performance low, and we'd like to get away from that for that reason. So interesting compare and contrast there. Cool. Okay, one more in this vein. I suppose I should put a title here. Maximalist approach to reinforcement learning from human feedback. This is just yet another paper that's come across the dashboard since we last looked at DPO, IPO, KPO, etc. This one has some good promises in the abstract, so I thought we'd take a quick look at it. Self-play preference optimization. Okay, so another very similar idea from the title. Reinforcement learning from human feedback. Minimalist in that we don't train a reward model. We don't have unstable adversarial training, and it's rather simple to implement. Great, we like to hear that. Our approach is maximalist in that it provably handles non-Markovian, intransitive, and stochastic preferences. Okay, big words. This paper, I seem to remember skimming this abstract and getting a feeling this is one of those where if you aren't up to date with your game theory literature and your economics and your reinforcement learning, there's a lot of terminology here that might be a little bit intimidating. But we'll try and figure out what some of these words mean, but also not get too stuck in the decision theory and instead just try and get an overview of this technique. Okay, so we're looking at social choice theory literature. Yeah, there we go. Zero-sum game. It's symmetric. So in other words, if you have two models, which generation is better, there's no like one-sidedness, there's no advantage to one or the other, so we can just say, okay, this is symmetric. So rather than having two different policies that are competing, which is often unstable, we can have a single agent play itself while maintaining strong convergence guarantees. That's great. It corresponds to sampling multiple trajectories from a policy, asking a radar or preference model to compare them, and then using the proportion of wins as the reward for a particular trajectory. Okay. Sounds like we might be a little bit deep in the reinforcement learning choice theory, but also that this might be a pretty promising paper, and they do keep saying simple, easy, minimalist. So let's take a look at the pretty picture. Okay, standard pipeline left. You train a reward model based on a data set of pairwise preferences. So I have some pairwise preferences here that have been labeled by a human or something. I train a reward model to predict some score or some likelihood attached to each one, which is good. And then I use that reward model to optimize my parameters of my base model using reinforcement learning. And that's often quite complicated and tricky. So they say we introduce SPO right, an iterative method that instead optimizes directly based on preference feedback provided by a rater or preference model, with each trajectory getting a reward based on the proportion of other on-policy trajectories it is preferred to. Okay, so this is going to be, rather than generating a bunch of data at the start and then doing your training, this is going to be continuous. We generate a few completions, we rate them, and then we update somehow based on that. Then we generate more completions, we rate them, we update. The on-policy part here is that these completions are both generated by the model we're training versus off-policy or any of the other like RL side things where you have a large data set that's like pre-computed. So now we're generating just some samples and updating before we generate the next ones. So if you want a human in the loop here, you need nice, efficient means. I guess that's why they're quite likely to want a robot rater. But as we've seen, just in the papers we read before, there's no reason a language model isn't a good judge, for example. So you could use the judging prompt from this paper to assign a score to both completions and then rank them that way. Cool. Okay, so that seems promising. Their technique does pretty well in some more OG reinforcement learning problems, which is nice. Assuming there's a single reward function that exists and that there's a total order to different completions, this is something that comes up when you're speaking about human preferences because, yeah, if you assume that there's always one best response that a model can give, then you're off to the races with a lot of the theory here. But in practice, if you're collecting data with multiple humans rating the data, or multiple like sets of guidelines, and not all of them are being interpreted correctly by people because they have different political biases and so on, you can end up with a case where prompt A is preferred to prompt B is preferred to prompt C, and prompt C is preferred to prompt A. Right? So that would be intransitive. And so that's unlike the case here where there's one perfect reward function that exists. It's like, oh, actually with human decision making, that's not the case. Especially if you've got multiple raters. So we need something that's able to not have this assumption of like one fixed perfect reward model / reward function, and instead deal with the fact that, you know, the real life is a little bit messier than that and still be able to learn somehow. Okay, and one way to do that is with this 2-player zero-sum games, but that's a lot of instability, and so that's the motivating factor behind theirs. We frame it as this 2-player zero-sum game where the two players are trying to compete to do the best response, but we actually have both players be the same model, right? So both of these are the same model producing these completions, but they're two different trajectories because you're sampling in different ways with a bit of randomness in there. And then your win rate is like, per sample, there's some preference. So this one is better than that one. Use that to update the policy to make those kinds of good responses more likely. Okay, so let's see. Here's a nice taxonomy and comparison. So DPO, for example, we have a fixed set of preference data that's been ranked beforehand, and we're using that to update the model later. PPO, more classic reinforcement learning online with a reward model. Their SPO, I guess it is also online, which is good. It fixes. Oh, it's okay. I see. So they're saying compounding errors. DPO is not robust to this because it's the data is generated first offline, the preference data, and often it's actually from a different model. Even people use like ultra feedback or something like that. So it's not generated by the model that you're training, and it's static, and so that doesn't necessarily hold it. As you train, your reward model is going to continue to be useful, and it doesn't guarantee robustness to intransitive preferences. PPO, at least you get some feedback from the reward model. You're not just using a fixed set of labeled pairs, but it has issues apparently with intransitive preferences. Theirs is the first that solves that. I'm less excited about these theoretical things, although I'm sure they are exciting, more that it seems like a nice framing for this reinforcement learning, where you're constantly generating and then evaluating those generations and using that rather than some static data set. Okay, so this is a very theory-heavy paper. One place you need for RLHF. That's great. Cool. Okay, so we have some number of iterations, some preference function, which would be your rating model or your humans in the loop. And I guess inspired by self-rewarding language models, we could even say, why don't we use a prompted version of the model we're currently training as our preference function? Might be interesting to try. And we're going to start with some policy. We have a way to go from that policy and some data to update. So that would be your standard RL update process, I guess. So we initialize our policy, running through some number of iterations. We sample, we compute a reward using our preference function. Set the reward to be, not quite sure what this step is doing. And then use whatever RL algorithm you were using to update the policy based on this triplet of, this is input, there's the reward. Okay, I'm not entirely sure, maybe this is like the RL notation. Yeah, make it so that it's more likely that you did the good one when you were sampling. I think that's pretty much the gist of this method. If there's any RL people in the chat, you can correct me if I'm completely off, but I think that's the idea here. Okay, so they do some experiments. There's is the orange. It does okay. The robustness to feedback being flipped. I'm not like deep enough or familiar enough with these like different tasks to know what's good or bad. But maybe for reinforcement learning people, that's great. I can ask my housemate's been doing some reinforcement learning recently. I can ask him what good scores are for cheetah and walker and hopper. I know he was training some good quadrupeds. Okay, so do they try this? I feel like this paper had results on some language modeling tasks, but maybe I'm thinking of a follow-on. Huh, maybe I am. Okay. Oh, well, in that case, we're very much open to seeing where this goes rather than seeing that this already works. For some reason, I remember that this paper showed good results on language models, but maybe that's a follow-on. But this was published 8th of January, so okay, I guess we'll have to wait and see. Bookmark this section in the long video for later reference. Cool. I'll take a quick break while we check in the chat for anything updating, and then we'll move on to the next section. Okay, gosh, we're already Alright, just realized we were already an hour in, and I do have several other meetings today, so I can't quite go as long as the previous Paperathon, but that's probably also good for everyone else's time, that we don't have another 4-hour video up on the YouTube. Okay, so in this case, let's... Yeah, so let's move from thinking about the preference side of things right at the end, and look at a few other papers. Okay, I guess I can clear these ones out from my tabs now that I've looked at them. Let's look at a few others that are bumping around in my head because of some recent discussions and work, and start thinking about the usage. So like right at the end, you've got your model, it's trained, what do you do with it? But then ways that you use that at the end, and trying to think how that could inform all the way through back to pre-training. We're going to skip this paper. This is an excellent paper. I actually, Alexander Long was sharing it with me, but I'm not going to look at this one. But yeah, thinking about the idea of how people use language models today, moving away from just this like prompt response and towards more retrieval and multiple tools being used and these kind of like agents that people talk about. What does that mean in terms of how we should be doing, for example, pre-training? And so I thought this paper was quite nice. End of last year, this came through. In context pre-training, language modeling beyond document boundaries. Yeah, so I think we'll look at this next, and then we'll quickly skim these two papers. So this is just a preview. We'll skip a couple of papers talking about like using these inference time techniques to improve things, and then we'll get to the DSPy that I know Jesse is excited about, as the library that's aiming to improve this idea, and I think that's where we'll call it for the day. So we're going to talk about in-context pre-training, and then some of the emerging approaches around inference time, multi-step, multi-hop reasoning, etc., and the tools that are emerging, and then we'll call that good. Okay, in context pre-training, language modeling beyond document boundaries. Large language models are currently trained to predict tokens given document prefixes, enabling them to directly perform long-form generation and prompting style tasks. Okay, so what this means is we train them one token at a time to predict the next token, and if you feed in 2/3 of an abstract, and then it's quite likely that the model will be able to complete the text in that same vein, and that's often useful if we feed in what looks like a number of questions with the corresponding answers, and then a question that doesn't have an answer. Maybe the language model will produce the answer, and as we've seen, we can also then start to fine-tune that for more explicit instruction following and so on. Okay, so they say that's the state of how we train these things, and existing pipelines just grab a bunch of short documents, they stuff them together, and that's our input. And we're going to be predicting on that. So during training, we're actually fetching bits and pieces from all over the web, all over different books and archive and PubMed and so on, maybe bits of code, and we're just shoving them all together, concatenating them. That's our string of text, and we're predicting the next token in that text. So their point that they make in this paper is that, well, that's not so useful, because if I'm predicting the next token in this abstract, but right before the abstract started, I had a web page on sales and marketing, or a car listing, or a piece of code, that wouldn't necessarily be useful. And so what the model's going to learn to do is like, oh, okay, I only look at maybe the recent context, and I ignore any preceding documents. And in this paper, they're saying maybe there's a new approach we should take, which is to have a sequence of related documents, so that you're able to attend past the document boundary into whatever the previous document was, and possibly have a chance of finding something that's useful, that's related, and explicitly encouraging them to read and reason across these boundaries. And the reason that this is useful is because if you think about how people do retrieval augmented generation, they tend to take a user query, and then they run off and they fetch, 3 or 5 possibly relevant pieces of text from their company documents, or from some data store, or from the web, and they shove that in to the start of the prompt, and they say, here's some context, boom, 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 basically 3 separate documents that are related to the user query, and they say, here's the query, produce the answer. And if your model's been trained to kind of only focus on the recent text and to ignore other documents before that, theoretically that might do a worse job at incorporating that context, or it might assume that that context has to be perfectly relevant because it's used to only looking at a whole document that's cohesive and then garbage before that. So you either get something that pays too much attention to the context and can be thrown off by erroneous context, or you get something that kind of ignores it. And neither of those are good. It would be much better if there was a model that was already like natively aware that you might see some related documents before the document that you're working on, and that you might want to pull some context from that if it's relevant and incorporate that in. So that's the in-context pre-training paper. They say this document sorting problem is challenging. There's billions of documents. So they're going to come up with some approximation algorithms for finding a good way to order those such that you have related documents together. And then they're going to try that and show that this pre-training is a nice way to enhance LLM's performance. And they show that on some tasks that require a bunch of contextual reasoning, this seems to give a bit of a boost. Okay, so that's a promising introduction. It's a promising technique. I think there's a lot of background and info in this paper, but the core idea is outlined in the abstract, and that I think is fantastic, but also that's pretty much all you need. So they're saying here is the standard language model training. I have a piece of context about the River Seine, and then one about FIFA, whereas if we ordered these with all FIFA-related, World Cup-related snippets being together, when the language model is working on this sequence and trying to estimate what comes next, it's got this context that, oh, in this previous document it mentioned that there was never a prize money above $10 million, and now there's a prize money of $40 million, so maybe the next words are, this is the highest ever. Whereas if your generation is from the sequence but you don't have any other relevant context, maybe it's harder for you to make this prediction. So that's their thesis here. If we can order our documents in the right way so that we have all the ones related to the World Cup and then all the ones related to Paris separately, maybe that'll help. Cool. So they train some models with a bunch of tokens from Common Crawl, and then they evaluate them on some downstream tasks. Yeah, so let's look at their process. Oh, we should also mention previous attempts have been made to do retrieval-based pre-training. I think Retro from DeepMind, for example. But a lot of those would just take whatever your current snippet was, they would find some nearest neighbors and then include those somehow. But that meant that there was often like repetition of neighbors that happened to be close to lots of others. It was a little bit more finicky and messy. Here, once you've done your ordering, you find related documents by clustering them or by finding similar documents for each one and coming up with an ordering. Once you've done that, your pre-training looks just like normal language model training. So the only fanciness is on the ordering of the data. You don't have to worry about how many neighbors should I retrieve, or what if I'm retrieving neighbors that have already been seen multiple times. Here, you can say, no, there's not duplication. There's not, there's nothing, no explicit retrieval. It's just that we've ordered these such that the preceding documents happen to be relevant. I see a question in the chat. Did we chat about DSPy? No, that's upcoming, hopefully. So we'll get to that, I'm guessing, in about half an hour. And then we'll take a quick look at the paper and maybe chat around that if people would like. That's just something, I've been using. So a lot of this paper backlog is actually related to thinking about how people use retrieval and multi-step reasoning and that kind of thing. So at the moment we're looking at in-context pre-training. And this paper, they have their method for ordering their documents such that related documents come together. So let's see the experiments that they do. The perplexity is lower, but this is sort of to be expected, right? Because it's easier to predict more tokens in the same theme that you've just been trained in, and that the current context contains documents relevant to that. More interesting for us is whether this improves downstream tasks. So let's see, they have, sentiment classification, hate speech, topic classification. Their in-context version outperforms the others. That's a nice bold bottom row. Oh wait, that's this one here. And then reading comprehension results using two-shot in-context learning. There's outperforms the baselines. Okay, so some nice solid metrics to back up their theoretical claims. Retrieval augmentation. Okay, so this is how people often are using these things in practice, right, at inference time. We're fetching a relevant set of passages, prepending it to our query, and so they can study some open question answering datasets, and see, how well the model does at answering based on the their pre-training versus normal versus other types of training. Okay, and here we see for question answering, their model does better than the standard, but it's not as good. Closed versus open is this. Oh yeah, so without retrieval is just directly answering the question, and the standard model does maybe even slightly better than theirs. But as soon as you prepend these contexts, like people are doing in practice, we go fetch relevant snippets, suddenly theirs is better. So that's great. Same thing with knowledge conflicts requiring better reasoning of the given context. Okay, so some sort of contrived data set where you have to use the given context. Again, theirs is doing a lot better than the standard pre-training, with the theory being that their training has helped it be more likely to be able to use some extra documents stacked on top. Cool. So I think that's pretty much all we have to look at for this paper, but I thought it was nice as a lead-in to this next section where we're talking about the ways people are using these models and the kinds of tasks we want to do. It's fun to see people thinking like, okay, given that that's how people use these models, are there things we can change about the pre-training to make these models better? There's lots of interesting thoughts to be had around whether you need this, how long your context should be when you're training, like whether this is wasting compute. But I do think it is an interesting direction, and it's nice to see, people designing these now with an understanding that, we don't just want to take all text on the internet, shuffle it up, and predict the next token, even though that does give you a pretty good base for future fine-tuning and downstream usage. Starting to say, hey, maybe we want better quality text, maybe we want to order it a little bit so that our model's good at reasoning across long context and fetching relevant information across document boundaries. It's cool to see this kind of thinking coming into the pre-training space, informed by some of the things people are doing downstream. Great. Okay. So speaking of downstream, a little collection of papers here, just showing some of the kinds of ways people use these models once they're trained. So this is now like inference time tricks rather than training. Okay, and so this one here from Google, I'm trying to remember which paper's which. Answering complex natural language questions often needs multi-step reasoning and integrating external information. So that's like the retrieval that previous one was talking about. Several systems have combined knowledge retrieval with a large language model to answer such questions, but there are some failure cases, and we don't train them end-to-end to fix such failures. So they're going to try and address that. They use a React-style LLM, which we can look at what React is, with the ability to reason and act upon external knowledge. And then we refine the agent through a REST-like method. We'll have to look at what that is, that iteratively trains on previous trajectories, employing growing batch reinforcement learning. Okay, so this is a more complicated paper than I thought. I think I was thinking of one of these baselines. This is almost tying more into the self-play and things as well. Okay, but nonetheless might be fun to look at. And I do love this Bamboogle eval. Cool. So let's see if we can dig through. Maybe we should look at React and REST just very quickly, see if there's a summary we can get of those. Wow, turns out we don't even have that in the library. Okay, so I feel like this is kind of in line with what a lot of people think about as agents. It's doing multiple steps, and it's evaluating and taking actions. I'm trying to see what distinguishes React from anything else. Maybe they've got an example of a prompt or something here. No, sadly not. Let's look at the example. Okay, so we've got some question in. If we just answer it, we get the wrong answer. If we do chain of thought, we get the wrong answer. If we train something to do things like search, we might end up with the wrong answer. Here we have something that's doing reasoning and action, so it's like combining chain of thought with being able to do things like call out to search functions and calculators and so on. So it says, okay, I need to search Apple Remote, find the program, so it does a search, figures out what it was originally designed to control, has a thought. Now I need to find out what other device can search that. Does a search. Oh, can't find the right answers. Does a search again. Try something else. Finally gets a result. So this is like a loop now, rather than just saying, oh, reason through your answers and then produce your thoughts and then produce an answer. This is integrating both actions and reflection, I guess, reason they call it. Okay, so that's one of the two components that's coming into this REST meets React. Now we need to figure out what the REST was. You can tell my speed really slows down after the first hour. Let's see if that one's in here at least. Reinforced self-training for language modeling. Oh, okay. Cool. I remember this paper. So very similar to some of the other ones we looked at, where we have generating some data and then refining that data, then generating more data with an improved model that's trained on that refined data, and so on and so forth. Okay, so that's good. So this REST meets React is not the paper that I thought it was, but it does look interesting nonetheless. We can go back to that and skim it. REST meets React, self-improvement for multi-step reasoning LLM agent. Okay, so we are combining something that is taking actions like search or retrieval, and then doing thoughts and reasoning on those to answer longer questions, and REST, which is this generating data, filtering it, and self-improving with this kind of like iterative reinforcement learning approach, just like some of the other ones we looked at today. So starting from a prompted language model, and just after 2 iterations of the algorithm, we get a fine-tuned small model that achieves comparable performance on challenging compositional question answering benchmarks with a lot fewer parameters. Okay. So this is like, how do we take a large model off the shelf that we can prompt? How do we turn that into an efficient small model by generating and bootstrapping our way through data, by having these kind of multiple steps and evaluations? And so, yeah, this is going from a generic language model to something that's very useful for the kinds of downstream retrieval augmented tasks that people do. Fantastic. Okay, so address the lack of and difficulty in obtaining multi-step human data. Right, we often, it's one thing to have an instruction and a response, it's another to have multiple thoughts and actions that you're annotating at each stage. So that's cool. We are going to use self-critique, AI feedback, and synthetic data, all good buzzwords. And they use this REST algorithm where you update based on some fine-tuning data, then you generate more data, but here they're improving so they're sampling from this latest policy, and then they're filtering that somehow using a reward model, and the reward model in this case is also going to be a prompted model. Okay, so state machine of the search agent flow, we have some question. We decide whether we need to call, so this is the act part, go do a web search, we summarize the result, we decide, do I need to do another web search, maybe summarize the result. Once we think we have enough info, we can generate the answer. We're going to self-check ourselves, we're going to check the grounding, like does this match the retrieved context, and then we're going to produce the final answer. Okay, so this is what I was hoping for from this paper, even though it's not the one I was thinking of. This is very different to just generate the next token and hope for the best. And so this is why we're looking at this paper. And the other one is that we're starting to think, what are some ways people use these models? And also to keep in mind, like, are there ways we could do our pre-training differently that might help this, or at least our fine-tuning? Okay, so they're going to use prompting. They're going to use a large model that can do lots of things without training. And then they're going to use various different smaller models as their actual models that are being trained. Usually produce multiple samples for each step and then select the one with the lowest perplexity to continue forward. Okay, so this is some sort of like pre-filtering way of generating the best possible training data for the next step. As a search tool, they use Google. That's great. They get some snippets returned back. We limit the total number of searches per agent trajectory. Okay, and then we've got some data sets to provide initial questions. Explain like I'm5, hotpot QA, multi-hop reasoning data set. And these are, a lot of these are constructed like, I can't just answer this one shot. It'll be something that requires maybe 2 or 3 searches and then aggregating that information together. Cool. Their ranking model is an instruction-tuned Palm 2 with a prompt. That's fine. Okay, so we start with a model, like prompted Palm 2, that's able to do this task just natively, right? So some big model that's been trained to follow instructions in general, and we tell it exactly what we want it to do. We collect reasoning trajectories. In other words, here's the input, here's a thought, here's an action, or whatever. So we're building up some training data that includes the reasoning. Convert this into fine-tuning. Apply re-ranking. So now only like pick the best ones, for example. And then fine-tune the new model on this mixture. And so this is like hopefully now improving because we've generated more data, we've only picked the best of that data, and then we train a new model on this, and you could do some of the ideas of self-rewarding where now you use that improved model as the next judge for the next round, etc., etc. And then once you've collected enough of these traces, you can also train smaller models on those sets of traces that bake in the reasoning. So they call self-distillation or distillation. We're generating these traces that include the reasoning and the reflection and so on, and then we can bake that into a smaller model just by saying imitate the reasoning of the larger model. The evaluation is really fun. They have this Bamboogle dataset. It is a dataset of 2-hop questions that were unanswerable by direct Google search. So what is the maximum airspeed of the third fastest bird? First, you kind of have to answer like, what's the third fastest bird? Then you can find out what its maximum airspeed is. And if you try and just answer that directly, there's no text on the internet that says the third fastest bird is 20 kilometers an hour or 320 kilometers an hour. They might say the golden eagle is 300 kilometers an hour, and separately they might say the fastest bird is the peregrine falcon, second fastest is the Lana falcon, and the third is the golden eagle. So it's definitely a tricky adversarial type of question. It's a really fun data set. Okay, and they have their own version because the original one was released, and so there might be some pollution, and also, you know, as is the nature of any measure, it's very tempting for someone at Google to say, ooh, Google gets this wrong, it'd be nice to change that so that it gets it right. So they have their own secret, separate Bamboogle dataset. Okay, so that's pretty nice. I don't think we need to go too much into the details here, other than, yeah, you're starting from a strong model, you're using that to generate data that you're then filtering with another model with that same strong model, using that to fine-tune again, and so on. And then once you have a good fine-tuned model and it's producing those trajectories, you can use that to train a smaller model to imitate that kind of reasoning and multi-step problem solving. And yeah, I think there's some nice graphs that show over self-improvement steps 1 and 2, they get a sort of boost in the quality, especially at the lower levels, right? So the smaller models here initially are pretty terrible, but then once you add and train on the self-improvement data, and you do a second round of that again, generating lots of responses, picking the best, etc., you end up getting better and better, and at some point your smaller models start to approach the same performance as the larger models without any training, so the just prompt-only large models. Okay, so that's REST meets React, slight diversion, but what's key in this paper and what I want to flag is that this is starting to look a lot more like the ways people use these models for large and more complicated types of problem. And this is moving further and further away from the vanilla, here's a question, I'll produce one token at a time, the answer. And so in that theme, the last 2 papers we'll look at is going to be another one doing this application specific, like code generation with this kind of technique. And then we'll look at quickly this library that claims to help be able to create these kinds of pipelines and then also to improve them. Thanks, Jesse, for the comment. He says he's going to miss the part that he'd been waiting for the whole time, so sorry about that. But this will be on YouTube. I think a lot more people will watch it there than live. But I do appreciate everyone who does come and join the live stream. I'll try and give even more notice next time. Okay, so code generation with alpha codium, from prompt engineering to flow engineering. Code generation problems are different from common NLP problems in that they require identifying happy paths, edge cases, small details, lots of code-specific issues and requirements. In other words, these are non-trivial problems. And a lot of the tricks that we do for general, like easy answering a question from general knowledge might not be applicable to code tasks. So they have a new approach that they call alpha codium, test-based, multi-stage, code-oriented iterative flow. Try saying that 5 times fast. That improves the performance of LLMs on code problems. They've tested it on a challenging data set. It improves results on validation set, increased accuracy from 19% with a good prompt all the way up to 44% with their flow. And they have a good blog post, and I think they have the code available as well. Okay, so they say generating programs is hard, especially if you only get a signal like correct or not, and you've done a whole lot of code to get there. programs, transformer models can do code to solve simple problems, but real-world ones are often difficult. AlphaCode is DeepMind's version, and there's AlphaCode 2 that generates a large number of possible solutions, and then only a small number of those is chosen and submitted. And they were able to do pretty well on some competitive coding tasks, but it's very tricky because you need a task-specific model. They do a lot of training, and then brute forcing a million solutions and picking the best. Very, very computationally intensive. So their AlphaCodium flow is going to try and improve that. Okay, so we see here another flow, again, moving away from just language model produces one token at a time, more into this kind of multi-stage, looping back, multi-hop reasoning, etc. style thing. So you have the input, a problem, a description, and some public tests. So this is from a coding challenges task. They have problem reflection. What is this problem about? What are the tests testing for? Generating possible solutions, ranking solutions, generating more tests, and then iterating on the code solution, the public tests, the private tests, multiple times if needed on each of those, and only then generating the final solution. So this is your classic, well, yeah, I say classic, this is like the new and emerging, it's a good example of the new and emerging pattern for using language models that isn't just one-off, one generation and done. It's this iterative, multi-step, lots of feedback, lots of self-reflection, trying to break everything down, validate individual steps. That's becoming more and more popular, and I think more and more powerful because it can get away from some of the limitations of vanilla, just produce the next token, produce the answer right away style problem solving. Cool. Okay, so that's the key part of the paper. They're going to talk, I think, a little bit about how specific to code problems, there's things like the example tests might not cover the entire space of the solutions, right? You might only get a few different tests, and so by generating more tests as a way to like validate their answers, they're able to get better coverage, and then they're able to make sure that when they do produce a solution, it is the correct solution. Yeah, we don't need to go too much into the details of the data set or anything like that. But what I want to highlight is that, yeah, this is another example of this long and complicated flow. And being able to use models for each of these parts of that flow, or to write, in this case, write tests that can be used as a validation step in that flow. Yeah, so it's a good example of that. Let's see. Yeah, random little insights like using YAML seems to work well for structured output. Seems like this is a paper full of good practical learnings, but yeah, we're mainly interested in how does this do versus just direct prompting. They can apply this to different models, which is nice. So this is an example of an artifact or a paper that isn't like, oh, we trained a specific model and here's how it does. It's like we have this new order of operations and here's how it does. And compared to the base direct prompting, they show a pretty sizable increase on just about all the tasks they evaluate. And yeah, showing, oh, here's our pass at 5 versus AlphaCode, which had to generate 100,000 examples and then pick 10 candidates from that. Pretty impressive. Yeah, 15 to 20 LLM calls per solution, and they're generally making 5 and then seeing how many of those pass or whether you pass or not given the 5 top. Yeah, so a lot more efficient than the original AlphaCode, which is, like I said, I think a million samples generated. AlphaCode 2 requires about 100 samples to reach the performance, so that's already also an improvement. We'll have to look at AlphaCode 2 sometime, I guess. But yeah, I really like this paper. I think they also have a nice accessible blog post. And the reason that I included this in the listing here, I'd skimmed it once before, but I wanted to flag as well this approach. And yeah, if you have thoughts in the document or in the chat on how you could do pre-training, like here we said, oh, we do some in-context pre-training by reordering the documents because we do retrieval. I wonder what kind of pre-training one would need to do to make language models that are even better for this kind of iterative, updating, multi-step flow style solution. And it's a very interesting question to think about. Can you even imagine what the pre-training data might look for that? Perhaps the answer is that it's more like synthetic data of this kind of iterative problem solving, right? So it's less like Wikipedia or something that already exists, and more, can we generate these kinds of maybe looking at GitHub commit messages or something like that. I don't know, something where you have multiple steps where people are iterating and updating. But yeah, very interesting to think about. But it also sets us up quite nicely for the last paper of the day. Thank you all for bearing with me and coming along on the ride. We're going to look at the paper for the software, DSPY or DSPy. I don't know how people say that. Compiling declarative language model calls into self-improving pipelines. This is a piece of software that I've very recently started tinkering around with a little bit. It seems like some people are quite excited about it as a way to bring a bit of simplification to their long and complicated code generation or other LLM applications. So we see, okay, we're rapidly exploring techniques for prompting. That's right, stacking them into pipelines. That's correct. That's exactly what we're looking at. But a lot of the existing ones are typically implemented using hard-coded prompt templates. That is also true. If you look at the REST meets React paper, let's scroll down to the appendices and see if we can find some nice long prompts. Yeah, here we go. So decision step prompt, this is a fragment of the prompt. Summarization prompt. Again, the actual prompts are even longer. Yeah, so that's the observation here, is that these lengthy strings discovered via trial and error are not exactly optimal. And also it can often make it hard to tweak your pipeline if you've got lots of big, chunky, one-off pieces of text defining what's going on. And so they are going to introduce an alternative, a programming model that abstracts these pipelines away into text transformation graphs. So that's pretty cool. Okay, it says they're parameterized. We can look at what that means. And they have a compiler that will optimize any pipeline to maximize a metric. And they have some case studies to look into this. Seems like a pretty cool idea and some pretty bold claims on social media. If you believe that, you'll see people saying, oh, I just used DSPy and my accuracy went up, yeah, from 5 to 46% or up by 65%. Yeah, we'll have a look at what that looks like and some of the larger claims. But yeah, let's dive in and see exactly how they address this problem. Okay, so we want a more systematic approach. They have a DSPy programming model that's going to translate strings into declarative modules, and then they have a compiler. So I think those are the main pieces. Let's see what they do. DSPy programming model. Instead of freeform string prompts, we use signatures to assign work to the LLM. A natural language typed declaration of a function. It's like a spec that tells us what text transformation needs to be done, rather than how it should be done. Okay, so here's an example here, I guess. We have a question as the input and an answer as the output. And so rather than trying to write our own verbose prompt that says, here is a question, answer appropriately, question, colon, here's a question, answer, colon, we are just going to specify the input-output transformation that we'd like, and then DSPy.predict is going to magically produce something that behind the scenes uses a language model to do this transformation. And when you feed in a question, you get back something that has an answer attribute, which is what we would hope for. Okay, so that looks interesting. I'm sure you, like me, are wondering what exactly is going on behind the scenes when you do something like this, and more generally how you would specify something more complicated than this one-liner. So let's see if we can see. Okay, so they're saying, well, once we have that, we can start to do more complicated things. They have chain of thought, program of thought, multi-chain comparison, and React. So presumably React, you can pass in some tools. Chain of thought, it's going to produce some reasoning before it produces the answer. Yeah, and so they say all of these models are using the existing one, and so their chain of thought is going to have some inputs and some outputs, and it's now going to add a field for reasoning. And It's going to create something called a signature, and then it's going to predict with this new version of the signature that includes the reasoning step. So some of this to me looks exciting. Some of this to me looks like a little bit more complication for people who are now using this. It's like, okay, between you and the actual language model are these multiple layers of abstraction. But yeah, I guess we can see if they expose that complexity anywhere. For now, I guess the takeaway from that first section is that, yeah, we can specify what we want, I guess, just by feeding in descriptions of the inputs and outputs, but not necessarily telling the language model what to do with those. Okay, and so they're saying, yeah, everything has some inputs and produces some outputs, and so that's all we need to pass in. And you can also use tools like retrieval, Python interpreter. Glad it runs in a sandbox. Cool. And we can chain multiple of these things into a single larger module. So here, generate answer is a chain of thought that takes a context and a question. Behind the scenes, I guess, produces some reasoning and then produces an answer. And the context is coming from a separate module which is doing retrieval. Again, it bugs me, like, it's not exactly clear what's happening here. I guess you could go and inspect what's going on, or you could try this and you hopefully get an error that says you haven't told us what retrieval method to use or where to retrieve from. But it is nice to be able to look at your overall flow, like this higher level picture, almost at something like this level rather than the prompt level, where you're saying, oh, I have a question, I transform it into a decision as to whether to do a web search or whether I've got enough information. So I have like a do web search question mark, and then if I have a web search, I go call the tool, and then I have a summary module, and that feeds back into the decision step, which takes, you know, maybe a list of previous searches as one of the inputs. Yeah, so it's trying to move us away, I guess, from handcrafted prompts to some higher level picture that lets us compose things into these chains. Okay, so that's pretty neat. Yeah, I guess this is possibly not the right venue for this. Maybe I'll have to do a separate video once I've explored more and know what's going on in the internals here, and have some ways to interrogate exactly what's going to the language model and how that works. But for now, that's a neat idea. It's a very appealing idea that one would be able to define these complicated processes just by specifying the inputs and outputs and having the library do the rest. And I guess even potentially do the prompting. So they have this second idea, which they talked about, optimizers and also teleprompters, which takes the program, something like this, and a training set and a metric, and returns a new optimized program. So if we think about this in the context of the examples that we saw here, I guess the original program might be this prompt-based version where you have a large model like PaLM doing the decision, choosing what to search, producing the answers, doing the checks, etc. And the compiled version might be like the smaller model that they then fine-tune on that data, which includes the full traces. And so here they say training examples may be incomplete. So for example, you only have the code and the solution. You don't have the intermediate reasoning steps or the tests, or you only have the query and the correct answer. You don't have the intermediate searches. But you don't need those, because in practice we're going to be able to generate them somehow. And that's going to be the trick that this pulls, I guess. Metric needs to be some measure of how it works. Bootstrap FewShot simulates retrieval on the training examples. It will collect demonstrations of each module. They collectively lead to valid output, and then we'd end up with a new prompt, perhaps. This compiled RAG would be a new prompt that included examples that worked well. So I guess that's one way of compiling it, is just to add some examples. I think here, yeah, maybe they'll explain more what's going on and what different types of compiler are available. Okay, so Bootstrap FewShot is just collecting some examples, including labels for the intermediate bits by assuming that anything that produces the right final answer had good good intermediate like traces. So that's great. Parameter optimization. Okay, you can pick the right ones. Another type of optimization is fine-tuning. Okay, that makes sense. That's more like the Palm example here. Demonstration I use to update the language model weights for each predictor. So we are able to somehow gather demonstrations, i.e. like full run-throughs of each trace with some large language model, and then update potentially a different language model via regular fine-tuning. Okay, and then this is just tweaking the program slightly. Cool. So, I mean, that's an interesting approach. Yeah, like I said, I need to dive more into the code, I think, before I do too much video on this. But I like that people are considering this, and it does provide like I said, an appealing picture of what the world could be, right? You say, okay, I have a question to an answer. That's my baseline. I don't have to spend time prompting and tweaking for each model. Maybe I can compile this so that it gets a few good examples and becomes a few-shot question to answer pipeline. And that's my like baseline, that I could use whatever language model I'm evaluating without spending time actually engineering the prompt. I just rely on this DSPy module to do its magic behind the scenes. And then if I would like to try more complicated methods, I can just use these building blocks that are going to do things like produce reasoning in the middle, or I can build up some more complicated class that chains multiple of these together, right? So now we're doing a number of completions, and then we're comparing them to generate the final answer. Maybe you add in tools here so that you have search and retrieval, then you have chain of thought that includes context, and then you have answer evaluation that looks at multiple answers and picks the best. And all of these become like a nice small piece of code rather than some giant convoluted, lang chain or manual prompting monstrosity. And for all of these, we can call .compile to somehow magically improve them by tweaking the wording of the prompts, by adding examples, or by fine-tuning from some large model into some smaller module. So that's a pretty promising future. I'm quite excited that people are starting to pick this idea up. And yeah, hopefully this is just another tool in the toolbox that allows people to explore these more complicated flow-based iterative multi-hop problem-solving approaches that are so promising for solving the kinds of problems that just don't work in a single left to right generative manner. Cool. All right, that was a lot of talking, but we're a lot less cluttered on my Zotero tabs. Still a few sticking around there, but they can always hang out for later. I will switch back to let's just call that done. I'll switch back, check the chat one last time. I don't see any outstanding questions. If you've made it this far, I'm amazed, I'm impressed. Thank you so much for watching. If you're watching this on YouTube, as I think most will, leave some comments down in the comments section if you have questions for me, if you have papers you'd like to see in a future Paperathon. I would like to come back and do some more focused videos. It's just a matter of finding time and balancing other responsibilities. So we'll see whether those come through. But these, like I said, are quite informal and thus quite easy to slip in. When there's a slow day, I haven't planned the rest of the week yet. And I've already got my productive work done in the morning. Nice to have a Monday afternoon stream. And good to clear up some of the Zotero backlog. Yeah, I hope these are useful. The goal with these, as much as it is for me to get through stuff, the goal is to highlight the kinds of ways you can read papers, right? None of these ones here did we go through every single word. Some of them we were able to dive a little bit in depth. Others we saw some complicated notation and backed out. That's totally fine. I find the process of research here is sometimes to understand something fully, especially if it's specifically like exactly what you need for solving some problem or for your job. But often it's also just building up a larger picture. And very rarely do you get a paper that has the whole picture. It's more that you start to see trends across papers. And so that's why I'm kind of jumping around and quick skim of REST and quick look at React. Okay, that's what those are. We have picture emerging of today, if we were to summarize, Um, Using language models to produce training data to improve the language models was a big theme. You see there's lots of people exploring different ways to do that. How do I start from some human data and bootstrap my way up? What if the problem requires multi-step reasoning? How do I generate data for those multiple steps so that I can fine-tune on that later? Are there ways I can evaluate as I make my model better? Maybe it's a better evaluator. You start to see these themes, and it's not like one paper came up with the idea of using the language model you're training as the judge itself as well. And that's, it's only that paper that matters. It's more like that zeitgeist is emerging, using these models against each other in self-play or as their own reward models, or using larger models to train smaller models, using them to evaluate traces and pick the best, filtering at every stage, making better synthetic data at every stage. You start to see these broad pictures that are emerging. And I think that's one of the reasons why I like to do these paper readings, is expressing that and trying to figure that out even while you're puzzling through the intricacies of what is the React framework. It's an interesting challenge, and it's quite different, I think, to, I just need to read this paper for that sake and then throw it away. It's a paper by itself. And even when I make a video on a single paper, it's easy to make that mistake. Just treat it in isolation. So I hope this has given you a bit of that larger picture. It wasn't a very well planned one this particular time, although it did end up with a good theme. If you have suggestions for what that theme should be rather than future papers, that's also something. Feel free to comment down below. And thank you so much for watching. We'll see you in the next one.